Hey folks, Todd Coburn here with your Aerospace Structures series. This video is part of Lecture 1 for our Dynamics online class. And in this video, we're going to cover Newton's laws. Now, we're going to cover the 3 laws of Newton. The first one says that if the resultant force on a particle is 0. Now, remember we talked in the last video, 1a, we talked about particles versus rigid bodies. So we're going to use that word particle to say, we're going to not worry about the overall size. Pretend that all the forces acting can be acted as if they're at the center of mass. So if the resultant forces on a particle are 0, it remains at rest, or it continues moving with a constant velocity. So if the resultant forces, so when we're talking forces, and if we add, resultant means we're adding all the forces together. Like we have a force this way, a force this way, right? Add them to this one plus this one. Or a force like this, adding these two together. Or adding these two together. We're talking about the resultant forces, which means we add all the forces acting on the particle. Whether we're talking about a little man, all the forces acting on him. A little man, all the forces acting on a little aircraft. Motorcycle, all the forces acting on it. If they all sum to 0, magnitude and direction, then either that particle remains at rest if it was already at rest, or else if it was already moving, it continues to move with the same velocity it had. So let's take a look at what that means. Let's say we have a particle, and let's say we have 2 forces. Now, we can see it looks like the 2 forces are equal and opposite, which means if we add them together. Now, in this class, as we did in statics, we're going to be summing forces. Typically, we'll say, what's the sum of the forces in the x direction? Okay? We can sum the force in the x direction, y direction, z direction. What's the sum of the force in the x direction? We add this p minus p, they equal 0. If the sum of forces equals 0, that thing stays at rest. It was at rest, it remains at rest. Now let's say there's a particle that's actually moving and the sum of the forces acting on it are 0. You see that was moving, the sum of the forces were 0, that means it keeps moving. The motion doesn't change. It was already moving, it keeps moving. Okay? Anytime the sum of forces is 0, this particle will either remain at rest if it was at rest or continue moving with the same velocity. Key principle. Seems kind of trivial, but it's a foundational idea that everything builds off of. Okay? Let's take a look at another example. So if we look at this guy, this cat is laying here sleeping, you'll notice nothing's really happening. Nothing's pushing on him, nothing's scaring him, nothing's doing anything to him. He is going to remain at rest because the forces acting on him are equal and opposite. For example, in this particular case, he has mass. Since he has mass, he has a weight that's acting toward the center of the Earth. And if we treat him as a particle, we know that Earth is pushing back with the exact same force. If it weren't, he would fall, and then he wouldn't be at rest. But because the carpet, in this case, is pushing up with the same force as his weight, the sum of the forces is 0. In this case, we're summing the force in the y direction. The reaction of the Earth minus the weight of the cat equals 0. Therefore, he remains at rest. Okay? That's our first principle. Another example that we can think of when we have an aircraft flying in steady flight. Notice this aircraft is flying with a constant speed. It's flying at a constant speed, and when this is happening, a couple things, our thrust is completely balanced. Our thrust is completely balanced by the drag. The thrust on it, in this case a prop aircraft, so it's pulling the aircraft along. The drag is resisting it. If the drag was less than the thrust, we would be accelerating. If the drag is more than the thrust, we would be decelerating. But since the drag and thrust are equal, we're running along at constant speed. So our sum of forces are 0. The lift is also completely balanced by the weight of the aircraft. Since this is moving forward through the aircraft wing shape is designed to provide an upward lift force at speed when it's got a forward motion. And meanwhile, the weight of the aircraft is pulling down. Now, if you want to get fancy or really precise, you'd find out that the CG of the aircraft needs to be in front of the center of lift for stability. We'll talk about that in a separate video. So and that's going to cause a tipping moment, which we now have to sum moments in order to get all the reaction pairs. But like I said, we'll deal with that later. Usually what we'll do is just pretend that these are lined up. We will just assume that that lift and that weight are perfectly lined up and there's no imbalance. And like this here, where you'll notice we back up, we're going to actually just simplify that by just assuming that the weight is occurring at the center of lift, or the lift is occurring at the center of weight. This is a way to treat the aircraft like a particle. So now we're not dealing with as a rigid body that can have moments applied to it. This keeps the analysis simple, and we can actually do a lot of really cool things with this. Do some really critical analysis just with this simple idealization. So the idea is this aircraft is flying at constant speed. To do that, that means there has to be thrust because there's drag. So the thrust and the drag are equal and opposite, and the weight of the aircraft is completely balanced perfectly by the lift. Okay, so that's that idea in that case. Newton's second law says if the resultant force, so this seems trivial, change, if the sum of the resultant forces, that means adding all the forces together, if we add them together and they're not zero, then we're going to have an acceleration that's proportional to the resultant in the direction of the resultant. So if the resultant force on a particle is zero, it will have acceleration that is proportional to the resultant in the direction of the resultant. So F equals ma. This is where this idea comes from. F equals ma. The force is equal, or sum of force is equal to the mass times acceleration. What this means is, if we sum up all the forces acting on a particle, and if they're zero, then it's not going to change whatever it's doing. Either if it's at rest, it stays at rest. If it's in motion, it stays in motion. But if the sum of the forces is not zero, we're going to get acceleration. And the acceleration is going to be proportional to the mass. Remember we said that the mass is like a resistance to change? So the more mass you have, the less acceleration you get. The less mass you have, the more acceleration you get. That's what we're talking about. So for example, we have this particle, and if we have forces applied, notice it looks like these two forces are not equal. If we sum them up, we're going to get something that's not equal. It looks like the force 1 is bigger than force 2. This means we have an imbalance. The sum of forces is not zero. It's going to accelerate in the direction of the larger forces pointing, and that acceleration is going to be proportional to mass. That's what we're going to be dealing with this semester. We just divide that summation of forces by the mass, and we'll know what the acceleration is. Okay? Got that idea? Another way to say the same thing is that the resultant force on a particle is proportional to the time rate of change of momentum. What does that mean? That our sum of forces, what we add together, all the forces, is equal to the mass times the change in velocity. Well, change in velocity is just acceleration. Acceleration is a change in velocity, and therefore we could say that the sum of force is equal to m delta v. This is the momentum principle. The other is the acceleration principle. We're going to first deal with the one and then deal with the other, and we'll go back and forth. And we're also going to deal with energy methods for some of these things, okay? So far, so good. Pretty simple ideas. We can do amazing things with these ideas, okay? Now, let's go back to our cat. Remember, before we saw him, and the summation of forces is zero because he's got a weight, and it's just feels good. It's like laying on the mattress. You ever lay on the mattress when you're tired and you just feel the mattress push back up against your body? It feels so good to be in equilibrium. Well, this dude's sitting here in equilibrium at rest, and then what happens? Some horrible professor jumps on the scene, and that dude is gone. The sum of forces were no longer zero. This terror force came into being, and that cat had a proportionate reaction. Okay? Sum of forces, but not zero. All right, another way to look at this in a more practical sense, let's say we have this aircraft that was in horizontal constant speed flight, and then let's say we get an imbalance on it. That means either the lift drops so that the weight is more, that means it's going to drop, or else maybe the drag increases due to wind or something, and so now we get a deceleration, or maybe we apply more thrust so it overcomes the drag and we get an acceleration, okay? So remember, at the constant speed, we were completely balanced, and our lift was completely balanced. And even though they're offset, we pretend that they're lined up, okay? Let's say we now give it more thrust, it accelerates. The summation of forces vertically was still zero, so it didn't change its elevation, but horizontally we had more thrust than drag. That provided a net acceleration in the direction of the larger force. Sum of forces was no longer zero in the x direction. Got that idea? Newton's third law, the forces of action and reaction have the same magnitude, the same line of action, opposite sense. Forces of action and reaction. Okay, we got this idea of action and reaction. That action word means we're applying a force, an applied force, or an action where the force is applied, like from a fist or a weight. Okay, we have the action and reaction. Reaction is what happens. Remember that cat? He's sitting there. His action force, his weight is acting down on the ground. The reaction of the ground is up. Okay? And these have the same magnitude. We always have to have a reaction that completely balances. If it doesn't balance, we're going to end up with some way of restoring that equilibrium, and that's what that acceleration does. That ma vector, the mass times acceleration, is a vector, is a force, and when we account for that, our sum of forces is back to zero. Our sum of applied forces, action forces, was non-zero. That caused an acceleration ma, or we could just think of it as subtracting out that ma gives a zero again, where we're getting equilibrium. So we'll talk about that more later. You may not quite be ready for that. So the forces of action and reaction. I press on the little man, and he pushes back with the same force. They have the same line of action because they're equal, right? We push like this, it's going to have the same line of action. The same magnitude and opposite sense, equal and opposite, okay? That idea. All right, let's look at our particle. That means if we apply a force, P, if that is at rest, we're going to have an equal and opposite reaction. In fact, even if it's not at rest, we could look at that as what's going to be acting against it is whatever forces are resisting it, plus the negative of whatever acceleration happens. We'll talk about that more later. So forces of action and reaction have the same magnitude, same line of action, opposite sense. Sum of forces, it's got to be zero. We're going to use this principle. This is called imposing equilibrium. We'll be drawing what's called free body diagrams like we did in statics, where we apply all forces to a structure to evaluate what happens to it. Okay? We're going to talk about this. Let's see. Sum of forces will always sum to zero. Okay. Because we have to have equilibrium, summing of forces has to be equal to zero, or they're going to equal ma, and when we count for that ma, they're back to zero, and we can use this to solve all kinds of things. We're going to be using this over and over again as we move forward. Okay? Let's look at some examples. So, first example, if you talk sweet to your girl, you're going to reap the benefits of that. Talk sweet, get sweet. However, if you talk mean, you're going to get mean. Okay? Action, reaction. Same magnitude, same line of action, opposite sense. Talk sweet, get sweet. Talk mean, get mean. If you can master this principle, you'll have a happy life. All right, let's look at Newton's law of gravitation. All right, this is a little more complicated than those earlier ideas, but it's related, okay? Two particles of mass. Let's say we have two things. Two things. They have different masses. Actually, it doesn't matter if they have different masses or the same masses. We have a big M and a little m, okay? The force, anytime we have a mass, there is going to be an attraction between the masses. They want to be together. Masses want to cling together. Take my word for it. Take Newton's word for it, okay? We can actually calculate just how much force of attraction through Newton's law of gravitation, okay? And the force is, if we know what the mass of the first thing is and the mass of the second thing, we can multiply those together, divide by the distance between them squared. So center of mass to center of mass, take that distance between them. This mass times this mass divided by the distance between them squared times a constant. We'll call the constant G. It's the gravitational constant, okay? All gravity is, we think of gravity as having to do with the earth, but all gravity is just a word that has to do with that attraction of different masses. The earth has a mass and you have a mass, therefore you're drawn together. It feels like the earth is pulling you to the earth. You're actually pulling on the earth with the same force. That's right, you have more influence than you thought you did. You're pulling on the earth with the same force that it's pulling on you, except it's a lot bigger, so you feel the force and it hardly does. This is what it's like in football. If you go pushing up against a bigger dude, you're going to feel it more than he does. If you are pushing on a little dude, they're going to feel it more than you do. So mass of the first one times mass of the second one divided by the distance between the centers of mass squared times the gravitational constant. Gravitational constant, there it is in US and SI units. So all you got to do, here's another little example down here this is from Beer and Johnson. This is from Wiley and Sons, Merriman Crage's book. If you have two masses, they have, in this particular case, you got some material. One's twice as big as the other. That means it has more mass. If it's the same thing, you look at the distance between. You just take the mass of the first times the mass of the second divided by this distance squared, multiplied by the gravitational force constant, and that's how much force is pushing on them. The little mass is pulling on the big mass by that amount, and the big mass is pulling on the little mass by that amount, okay? These forces, as we see here, they're drawing them together. You can practice this with your wife or your girlfriend. You're standing here, she's over in Canada, you get a little closer, you get a little closer, the closer you get, the more love you feel. Proximity causes the force to grow. So what does that mean? That means these dudes feel more attraction than these dudes. Why? More mass. Now, a lot of times I'll have my students stand up and get next to each other to see if they can feel this force of attraction. And a lot of times I see them leaning away from each other like they really don't want to be close. And then you can say, this doesn't work. There's no force. Well, actually there is. If you take their two masses, multiply them together, divide by the distance between their centers of mass squared, multiply by the gravitational constant, that is the force that's attraction. It's a force of attraction between them. However, if they have bad breath or stinky body or some other gross thing, you might have a different force of repulsion that's larger than the force of attraction. This is why sometimes we don't feel the love as we get closer. Sometimes we feel something else because there's some other force coming into being. You got it? Okay. So that's our second video for lecture 1. Got a few more to go. Make sure you watch them in sequence before you move on. Enjoy.